Hello, long time no see, guys. I came back. So, in the last part, we finished the frame, and now it's time to make this thing actually work, not just mechanically, but as a complete system. Before implementing any driving system, I decided to install the braking system first. The reason is simple. In any mechanical system that involves motion, control must be established before power. If the system can move but cannot stop, then it is not a system, it is a risk. So the braking components were aligned first. The brake disc had to be positioned concentrically with respect to the axle. Even a slight eccentricity would result in uneven braking force that would cause vibration during deceleration, and over time it would damage the entire assembly. So I manually aligned the disc and fixed the caliper position relative to it. The clearance between the pad and the disc had to be consistent, not too tight to avoid drag, not too loose to maintain braking response. This process required multiple adjustments, tightening, releasing, realigning, and checking again until the system behaved predictably. Once braking was secured, I moved on to the drivetrain. This is where the system transitions from electrical input to mechanical output. The motor was mounted first, but mounting the motor is not just fixing it to the frame. The shaft alignment had to be precise. If the motor shaft and the driven shaft are not aligned, it introduces lateral forces. Those forces translate into vibration, and vibration reduces efficiency, increases wear, and eventually leads to failure. So the motor position was adjusted multiple times, visually aligned, then mechanically verified. After that, the sprocket and chain were installed. This is a simple system in theory, but in practice, it is highly sensitive. Chain tension had to be tuned. If the tension is too low, the chain disengages under load. If the tension is too high, it increases friction and reduces the effective torque delivered to the wheel. So I adjusted the tension manually, pulled it, released it, measured the slack, checked rotation, and repeated that process until the motion became smooth. At this stage, the mechanical system was ready, but before building the final battery pack, I needed to verify whether the system actually responds. So I connected a temporary battery. This was not designed for performance. It was only intended to check basic functionality. Power was applied the motor started rotating, the chain engaged, and the wheel began to move. That confirmed one thing: the system works, at least at a functional level. Now, this is where the entire system starts to take shape. The battery pack. I went directly into the welding process and immediately welded into the structure. This approach saves time, but it increases risk, because once a weld is made, it is not easily reversible. So every contact point had to be verified before applying current. Then the welding begins. Spot welding looks simple, but in reality, it is one of the most critical and sensitive processes in battery fabrication. The welding energy must be controlled precisely. If the energy is too high, the internal chemistry of the cell is affected. That damage is not always visible, but over time, it leads to capacity loss or internal failure. On the other hand, if the other energy is too low, the connection becomes weak, and a weak connection introduces resistance. Resistance is not just a loss. At high current, it becomes heat. So every weld was applied carefully. So the next step was integrating the BMS, the battery management system. It's not just an accessory, it is a fundamental requirement. Without it, this entire system is unpredictable and unsafe. Each balance lead was connected individually, carefully, because a single incorrect connection can cause incorrect voltage readings, and incorrect readings lead to incorrect control decisions, which eventually leads to failure. In a 24S system, this becomes even more critical because voltage imbalance does not stay constant, it accumulates, and over time it becomes a serious problem. So every connection had to be stable. Now, the system moves beyond just the battery. At this stage, it becomes an integrated power system. First, the ESC was installed. The electronic speed controller is responsible for converting electrical energy into controlled motor output. Next, the DCDC converter. This component steps down the main system voltage to a usable level for low voltage electronics. In a 24S system, the voltage level is too high for most auxiliary components. So stable conversion is required. Then the relay system. Relays are not just switches, they define how power flows through the system, when power is applied, when it is cut, and under what condition the system is allowed to operate. In high current systems, now this becomes critical because a direct connection without control net means uncontrolled current flow, and that can damage components instantly. So relays were installed to manage power sequencing, ensuring that current does not surge unexpectedly. and that each subsystem activates in a controlled manner. Now, all major components are physically installed, but the system is still incomplete because nothing works without proper wiring. This is where most systems fail, not at the component level, but at the connection level. High current wiring was routed first. These lines carry the main power flow, so they must be short, direct, and mechanically secured, because any movement introduces stress at the connection points. Then low voltage and signal lines. These are far more sensitive. If placed too close to high current lines, they pick up noise. That noise affects control signals, which results in instability, so separation was maintained. Power lines and signal lines were routed independently. It was done for reliability. Each cable was fixed, each connector was checked, each path was verified, because at this level, a loose wire is not a small issue, it is a failure point. Now, everything is connected. Battery, ESC, DCDC converter, relays, all integrated into a single system. At this point, this is no longer collection of components. It is a functioning power architecture. Close the power system. Now everything is in the power box. AT next video. I will place everything, a battery place, and all of the power units. It will be the real test. Subscribe and stay tuned. See you next week.